Welcome to the chapter on renal dosing. It is reported that most hospitals around the United States have renal dosing programs run by pharmacists. Alerts of reduced renal function in patients lead to examination of the medication profile by pharmacists to determine if drugs are being administered that are primarily excreted by the kidney. In this video, we will examine an approach to estimating new doses, intervals, or both for renally excreted drugs when a patient has diminished renal function. I hope you enjoy the video.
Let's solve a patient case. A 50-year-old male patient who has an estimated creatinine clearance of 50 milliliters per minute is going to receive cefoxitin, and the order is for 1 gram intravenously every 8 hours. The FE, or fraction excreted unchanged in the urine, for cefoxitin is 0.8. Due to his diminished renal function, the dose should be altered from that given in normal renal function. So, rather than using 1 gram every 8 hours, what dose, in milligrams, would you suggest be given every 12 hours to accommodate for the patient's renal function? Let's look at the impact of reduced clearance on concentrations after a single dose. So here you see in normal renal function the drug being eliminated. When renal function is diminished, you will see changes in the elimination of a drug that is excreted primarily or at least to a significant degree in the urine. So in this case, you can see that the volume of distribution didn't change because the peak concentration is similar, but the half-life did change. There are many other options though. Here's an example where the volume of distribution got smaller and the half-life didn't change much. And here's another one where the volume got larger but the half-life was even longer. The main thing to note is that clearance of the drug will be less when creatinine clearance is diminished for drugs that are excreted to a large degree in the kidney. Here are the general calculations we can use. There are obviously a lot of other ways to dose patients in diminished renal function, including a variety of nomograms that may accompany the packaged literature or dosing strategies that come from the literature. In this formula, Q, or the dosage adjustment factor, is equal to 1 minus Fe, the fraction excreted unchanged in the urine, times 1 minus Kf. And Kf is the kidney function relative to normal. So the reduced creatinine clearance over what's considered normal creatinine clearance, which is generally accepted as 120 milliliters per minute. So let's plug in the information. Here's the formula again, 1 minus Fe times 1 minus creatinine clearance reduced renal function over normal. And then here are the values. If you remember, Fe for cefoxitin was 0.8. The patient's reduced renal function, 50 milliliters per minute over 120 milliliters per minute, which is considered normal. And once you plug those in, you come up with the dosage adjustment factor of 0.533, or in other words, about half of the normal dosing is needed in this degree of renal function with that Fe. Just some tips on this. Make sure that calculations are done within the brackets first and then multiply by the 0.8. Ensure that that's completed and then subtract from 1. It's pretty easy to make some errors in this type of formula if you don't pay attention. So the Q is 0.533, again indicating about half the dose is needed over a period of time. The formula to calculate the new dose and relative to the new interval is dose in reduced renal function is equal to normal dose times the dosing interval in reduced renal function over the normal dosing interval times the adjustment factor. So with the numbers in, The normal dose was 1 gram or 1,000 milligrams times the new interval we want to use, 12 hours, divided by the normal interval of 8 hours times the adjustment factor 0.533. And that tells us to use a dose of 800 milligrams. Most people would probably round that to 750 milligrams every 12 hours. Now, what's the impact of a smaller dose and increased interval on concentrations at steady state? And you should note that the goal is to have an average steady state concentration that's about the same for the reduced renal function as it would be in normal renal function. So here you can see I put in the normal dosing strategy where we have the CSS about the midpoint. And then here's a case where we have reduced renal function, and we might anticipate that the peak concentration would be a little bit lower and perhaps the trough concentration a little higher, but there could be wide variation in the way this curve would look. The key is that clearance of the drug is diminished and reduced renal function when the drug is eliminated by the kidney. Now, it is also possible to alter just the dose or just the interval. Obviously, it has to make sense, though. If we want to alter just the dose, we use the dosage adjustment factor and we keep the interval the same. So the dose in reduced renal function is equal to the normal dose times Q, or in this case, the normal dose was 1,000 milligrams times the 0.533, and that would tell us to use 533 milligrams every 8 hours. Obviously, that would be rounded off to 500 milligrams. Using this formula can be impacted by the dosage forms available. So as an example, if only 750 milligram tablets were available, you couldn't actually reduce to 500 milligrams. If you just want to alter the interval, then the interval tau in reduced renal function is equal to the normal tau divided by Q. So in this case, that would tell us to use an interval of 15 hours. And that's where things get even more complicated because you have to use something that's logical. You would want to go, as we did earlier, to 12 hours as the most likely scenario.